Welcome. My name is Rafe Levine. I'm a research software engineer on the Google Fonts team, and I've been doing lately a lot of research on how to render 2D graphics effectively on GPUs, and for that I have been using compute shaders quite extensively. So this is a talk on compute shaders, basically a 101 introduction. And my goals are to introduce the concept of compute shaders and get across a little bit of how to get started. Like, hopefully by the end of this, you'll have enough background and information that you can start writing your own compute shaders and get some experience. So the first question is, why do you even want to do general purpose GPU computing? And the reason why is very simple. General purpose GPUs in general give you about 10 times the compute throughput, whether that for the same cost, whether that cost is measured in dollars or watts, it's about the same over doing the same compute task on a CPU. And that improvement, that 10x improvement, is actually over multi-threaded SIMD code. Single instruction, multiple data code, which is not that common. A lot of people just write a single-threaded scalar code running on CPUs, and the compute bandwidth of a GPU is easily 2 orders of magnitude higher than that. So that's an enormous amount of compute capability that's sitting there on your computer waiting to be used. So I've said 10 times, and that's actually a surprising number. How do you really achieve 10 times the compute throughput compared with a CPU? Why can't CPUs just give you that level of throughput on its own? And it really is a function, they haven't changed the laws of physics, that it really is a function of what do you optimize for. That a CPU is heavily optimized for single-threaded performance, trying to extract parallelism, but spending a lot of transistors on superscalar issue, branch prediction, registry naming. There's a lot of tricks that CPUs do to try and get as many instructions in a sequential stream actually executed in parallel. And that's very expensive. That burns a lot of transistors, and you end up, with hugely more transistors than a CPU 10 or 20 years ago to get a relatively incremental performance improvement. So what GPUs do instead is that they spend those transistors on creating a lot of cores. So each individual core on a GPU is fairly low performance. But there's a lot of them. And so it's only geared towards workloads that have a lot of parallelism in them. Another technique that GPUs use is hiding latency. So one of the things that really slows down performance is access to memory. You do a memory read, and you can't do any work until that read comes back. And the latency for a memory read is typically in the hundreds or even thousands of cycles. So what a GPU will do is that it will have multiple threads that are potentially ready for execution at any time. And when you do a memory operation and you need to wait on it, instead of stalling it, you just take another one of those threads and start working on that. So again, that requires a lot more parallelism in the workload in order to have those threads available to run. GPUs have a very wide SIMD. 32 lanes is common, although that varies. And the idea is that all of the execution dispatch work, deciding which instruction to execute next, decoding it, getting it ready to run, you amortize that. You don't do it for every single instruction, or you do it for every instruction, but the instruction operates on 32 units of data. So the amount of dispatch that you're doing per unit of data is much, much smaller. And then the other thing that GPUs do that's very different than CPUs and changes the programming model is that they explicitly expose the memory hierarchy. On a CPU, you generally just say load or store to memory, and it might be stack, it might be heap, but from the point of view of the instruction that you're using, the programming model, it's all the same. and all of the caching and stuff like that that goes on under the hood is hidden from you. But on a GPU, there are explicitly layers of memory hierarchy. The fastest layer is the register hierarchy, and registers are kind of intermediate between just being registers and being memory. There are a lot of them. There are about 2 kilobytes worth of registers per thread, and because of the very large number of threads, that means that the total amount of memory on a GPU chip for the register file is quite considerable. The bandwidth is astonishingly large because each execution unit has its own dedicated register file. And so all of the execution units, of which there are a large number, are reading and writing their register file at a very high bandwidth. So that's in the tens of terabytes per second. And the latency is similarly a clock cycle or so. The next level of hierarchy, and this is something that you do not see on CPUs, is this concept of shared memory. So a work group, we'll get into work groups a little bit later, is a group of typically a couple hundred or 1,000 threads, has this 32K buffer of memory, and all of the threads in that work group can access that work group memory and coordinate work between them. And this is intermediate between registers and global memory. That there's typically a few terabytes per second of aggregate memory, and the latency is larger than registers, but considerably smaller than global memory. Then, of course, there is global memory, and usually on a GPU, it's a few gigabytes, depending. It's pretty extensive. The bandwidth is a lot higher than you would expect off of a CPU. That's a lot of the sort of cost of a GPU. And the latency is really large. It's in the thousands of clock cycles. So I have a question in the chat. Wouldn't the many SIMD lanes affect the actual count of registers, limiting the amount of heterogeneous data you can keep in the registers? And the answer is yes. That this talk, I'm not going to go into performance in detail. I'm hoping that there will be a follow-on talk for that. But it is true that registers are a scarce resource, and if you use too many of them, that reduces occupancy and reduces performance. So when you're using general purpose, so the reason why you want to use general purpose GPU is pretty clear. You want that throughput, you want that performance. But there are choices in how you get there. It used to be the choice was pretty clear. You would use OpenCL, which is a standard for accessing the compute power, the compute capability of a GPU. Unfortunately, in recent years, it's stagnating. The vendor support for it is poor. And when you look at projects like the renderers in Blender, they tend to be deprecating their OpenCL ports. So it unfortunately doesn't look like it has a good future. The choice that is almost universally used in machine learning, scientific computation, etc., is CUDA, which is an NVIDIA technology. It is very mature. It has excellent tools. There's a lot of knowledge out there, a lot of code bases, a lot of tutorials. It's pretty easy to get started. And so it's clear why it's such a so overwhelmingly a great choice for just getting access to the compute power. It is practically NVIDIA only. There are ways to run CUDA workloads on other graphics cards. There's Cycle, which is an evolution of OpenCL. RockM is an AMD API. One API is kind of Intel's solution to this, with aspirations to becoming actually cross-platform. But if you go out and you look at the renderers that are used in Blender and people trying to get them to work on hardware that other than NVIDIA, people are not having very good success with that. So the third choice, and what I'm going to be focusing on today, is to use compute shaders. And these are widely used for games, 3D engines, but relatively rarely used in other places. And I'm going to go into a lot more detail about the trade-offs and the potential. I feel like compute shaders have an enormous potential in the future. The main advantage, we'll go into this a little bit later, is that compute shaders are supported by all current graphics cards. And then there's challenges that there's API diversity. There isn't just one way to get to them. There's several, depending on what system you're running on. And then one of the other things that's happening in this space is that WebGPU is an upgrade over WebGL, that one of the main new features that it supports is compute shaders. It is in development. It is very promising, but it is not ready for prime time yet. What is a compute shader? And I'll go real quick through kind of the history of this, that in the 1900s, GPUs had a fixed function pipeline. So you would have logic on board the GPU to compute lighting, shading, etc. And that was all hardwired. There was no real way to control that in a fine-grained manner. So in 2001, the GeForce 3 came out with a programmable pixel shader, which is a small program that runs for every pixel in a triangle. The graphics folks are going to say it's a fragment shader. Fragment and pixel are basically the same for the purpose of this talk. So that was an enormous step forward. And as GPUs developed, that many different kinds of shaders are available for basically giving you programmatic control over different parts of the rendering pipeline, vertex geometry, tessellation, etc. And then CUDA came out in 2007 with a way to access the programmed capability, the parallelism of the graphics card. And that was followed up a couple of years later by Direct Compute, and then OpenGL a few years after that, which give you access to running the same kinds of programs, that's why they're called shaders, as pixel shaders, but organizing them in a grid and giving you access to random access read and write capability to buffer. So it really looks more like a program and less like a part of the graphics pipeline. And these days, compute shaders are available in all modern GPUs, all modern graphics APIs, and that's what a compute shader is. It's a way to access the compute power of a GPU through a primarily graphics-based API, although you do not have to be doing graphics to utilize the power of a compute shader. It's easier. Let me see if I can do this, that my face is covering up that word API. Sorry about that. So again, let's go a little bit into this sort of choice between CUDA and compute shader and what the difference is between these two. CUDA is single source. There is one C++ code base which covers both the host code, the code running on the CPU, and the device code, the code running on the GPU. And it tries to make the distinction between those as smooth and transparent as possible. So there is, in modern CUDA, a single address space for buffers that they're both host and device buffers are allocated in the same memory space. And if there needs to be copying between those are handled for you automatically by virtual memory. So there's a unified memory abstraction. Calls to kernels look like function calls. I'll give a slide in a second that shows that. And there's really an orchestration where the language, the CUDA, C++ extensions, the runtime, the driver, and the hardware are all working together to create this abstraction, to create this illusion of one unified computer that has both CPU and GPU components to it. The compute shader model really looks like remote procedure call, that the CPU and the GPU are two different computers. You write the programs that run on the GPU in a shader language like GLSL, Wixel, which is the WebGPU shader language. It's a different language as your host code. These are pretty low-level primitive languages. They're missing a lot of functions, a lot of features. And then when you want to get the GPU to do work for you, there's an explicit dispatch. And that dispatch resembles an RPC, a remote procedure call, where you're submitting work to a remote computer quite strongly. And one of the main ways in which that's true is that you submit the work and then it comes back at some later time. So the completion of that work is asynchronous. And then there's usually an explicit copying between a host and a device buffer. So you upload the work that you want to do, you dispatch it, the GPU goes off and does it, you wait for it, and it completes sometime later. So let's look at what this looks like. And the CUDA code on the left is actually a fragment of real code. And so there's a function that's annotated __ global, which means that it could run actually on the host or on the device, either way. So it's often you write the code in C++ when you're developing it, debugging it, and then you make it work on the GPU later. And it's just this annotation that says, hey, this code can be running on the GPU. And if you look at that code, it's pretty standard C++. There are pointers for the data. And then when you look at how you dispatch it, it looks like a function call with one special additional thing in those triple angle brackets is a grid saying, don't just call this function once. Create, in this case, a 2D grid of 128 by 1 threads. It can be 2D, 3D grids, but it's always a grid. It's always a fixed width and height and possibly depth. And it creates a thread. It creates multiple threads, one thread for each point in that grid, and runs that GPU code over that. Now, on the right, there is some sample code that you're going to be able to, that I'll link later, where you're going to be able to see the real code for it. But this is just pseudocode because there's a lot more going on where you have to get access to the device, create a pipeline, create a command buffer for submitting the work, create descriptors, dispatch it. The dispatch looks kind of similar, that you're also specifying the grid size at that point. Then you submit the command buffer, you wait for it to come back, and if you need to read the data, then you do some buffer-to-buffer transfer. And I haven't shown what the GPU side of that looks like, but it's in a different programming language. It looks pretty similar to the CUDA, actually. It's shader languages tend to look like C, but it's a different code than your host code, and you cannot easily move between the two. You can't easily start writing your code on the CPU and then get it running on the GPU for performance later. So, given that they're so much more painful to program, why do you want compute shaders? And the main reason is compatibility. The compute shaders are available on all GPUs that you can buy today. Okay, so that's zero, but that's a separate problem. So it is available on all modern GPUs, all GPU APIs, but the compatibility landscape is complex. The capabilities vary from GPU to GPU, and newer ones have more capabilities, and so you have to do some runtime query of that. But there are some other advantages to compute shaders. So there's very good interoperability with graphics rendering. So if you want to combine compute shaders and other rendering tasks, then you can do interop with CUDA as well, but with compute shaders, it's especially nice. And I think that's one of the reasons why the main usage of compute shaders today is in the game engines and 3D rendering tasks. One of the other things that's interesting about compute shaders is that they are improving fast. If you look at what was available maybe 2, 3, 5 years ago, it was quite primitive compared with CUDA, but that gap is closing. And there's a lot of features that have come out in compute shaders just in the last couple of years that really move it forward dramatically. So there is an explicit memory model that allows atomics with explicit memory semantics like acquire and release. That's relatively recent. It's still rolling out. It's the explicit memory semantics are only in Vulkan. They're not in DX12 or Metal yet, or WebGPU. And even within Vulkan, approximately 50% of the drivers on Windows and 25% of the drivers on Android in the vulkan.gpuinfo.org database have the memory model extension turned on. Also, recently you have access to 16-bit floats, 8-bit integers. This is extremely important for machine learning because you can get dramatically higher bandwidth by using smaller data types. And you generally only need those smaller data types to do machine learning, especially inference. And another feature that I'm throwing in there is descriptor indexing, which is the ability to access arrays of buffers in a sparse way. So I would say at this time, you can exploit most of the compute power that's available in the GPU through compute shaders. I would not have made that claim a couple of years ago, but I think today there's relatively little that's available on the GPU that you cannot access through the compute shader. And then in the future, I think this, the fact that it's not single source is potentially an advantage because you will be able to use other high-level languages, other abstractions, and compile those into compute shaders. And those abstractions include IREE, which is an intermediate representation for TensorFlow. So I expect that to be used a lot for machine learning workflows. And then one of the other really exciting projects to track is Rust GPU. And that in some ways gets you closer to the single source world because you can write your shaders in Rust. In some cases, you can compile them and run them on the CPU before porting them to the GPU. And Rust is, I'm a little bit biased, but Rust is a much higher level, much more pleasant language to develop in than the shader languages, which really show their C roots strongly. So why not compute shaders? Well, the tooling is very primitive. The developer experience of writing for compute shaders is quite painful, especially compared with CUDA, which is so much more mature. Portability and compatibility is challenging. There isn't a single API that you target. There's multiple ones of them, and there's a lot of challenges. There's a lot of detail that you have to take care of that you might hope is just abstracted away from you, but that hope is not yet realized. And so again, like when you talk about advanced features like access to scalars that are not 32-bit, those are optional. So you have to query, can this GPU support that? And then you might have to switch between two different code bases or do some sort of conditional thing depending on whether that feature is available. Drivers are buggy. The idea that GPUs just work is not true yet. And so when you look at applications that run on GPUs, they almost invariably have a quirks list or an exclusion list that says, if I'm running on GPU X with driver less than 1.2.y, then don't run or fall back to some compatibility mode because it's just super, super common that you run into driver bugs. And often they're exciting. Often they you need to reboot your computer when you run into these bugs. I've had that happen multiple times, and that's a common experience. So, needing to support this diversity is a source of complexity. There is no standard runtime out there. There's nothing that's like a rendering engine that's a standard for running compute shaders. I do have hope that WebGPU could fix this, but it's not quite there yet. And then performance also can vary from GPU to GPU. I had a blog post on a particular mobile GPU that was having surprisingly poor performance and how I track that down. And so you have to expect to spend time debugging and figuring this out. And then the programming model, again, is having to have separate code for your CPU and GPU. It's unintuitive. The shaders are in separate source files, different language. Getting work done is very explicit. The way you dispatch, the way you schedule it. There's a lot of ceremony. The Hello World examples are much bigger than I think they should be. And again, for a little bit more background on this, that SpireV is a common intermediate representation for compute shaders, and I just linked a blog that shows some of the things that make that challenging. So I'm going to go pundit a little bit before diving into the how a little later. I actually believe that compute shaders will disrupt this single source model. I believe the disadvantages are opportunities, that we can make tools better, we can figure out how to make the experience good, and the advantage of portability is compelling. I think WebGPU has a pretty good chance of becoming that standard runtime. It is forcing the vendors to come together, and that not all vendors are on board with open source standards for interoperability, and WebGPU is kind of the one place where all of the vendors are coming together and saying, we will run WebGPU on our GPUs, and we will basically compete on how well we do that. Now, there are risks. One of the big challenges, because you are downloading potentially malicious code off the internet and running it on hardware with a very large potential attack surface, there are a lot of concerns about security and also privacy, fingerprinting, and addressing those concerns might require performance compromises, and that would be disappointing. I'm hoping that they work that out so that you can actually achieve the security that's needed without major performance downgrades, but we need to see that to believe it. And when you look at like the W3C, the World Wide Web Consortium, trying to get adoption of new technology through the standards process, sometimes it hits, sometimes it misses. But I do believe, even though the tooling is very primitive today, that I think that it really has a lot of potential to improve. And I recommend, there's some academic work on like fancy parallel languages, and that's all good and it's exciting, but I really think that we need to be focusing on the lower layers first. Like, how do you represent a workload in a standard way and get it to run consistently, reliably on the GPU hardware on your device? But even though I feel like there's a lot of room for these tools to improve, you can use them today. You can utilize compute shaders to get that performance improvement today. And I'm hoping that basically the rest of this talk is going to tell you how to do that. So this is just kind of a very high-level architectural overview, that you don't directly run code on the GPU. You always go through some intermediate runtime layer. So if that's CUDA, then you have a CUDA runtime, and your application code has CUDA code in it, and ultimately that is going to connect to the GPU and run on that. And if you're using a compute shader, you're going to be using one of the graphics APIs, Vulkan, DX12, Metal, and you usually want to have a layer on top. Obviously, you can program directly to those, but you usually want to have some layer on top of that. And one choice of that layer is WGPU, which is the Mozilla implementation of WebGPU. And there's also a runtime that I've been working on lately called GPU HAL, which is a lightweight compute-only or compute-focused abstraction over those APIs, and I'll be talking about that as well. My face is obscuring the word metal, so you can see that. All right. So I'll turn my face off so you can see DXIL. So the landscape of shader languages and the kind of translations, transpilation between them is really complex and messy. There are many different source languages for shaders. There are many different intermediate representations. You don't write the assembly code for the GPU. You write an intermediate representation, which is somewhat standardized. And then the driver compiles that intermediate representation to the actual assembly code or binary code that's running on the device. So there is a standard SpireV for intermediate representation, but that's only used in Vulkan. It's not used in DX12 or Metal. They have their own intermediate representations, which are actually quite similar, but incompatible. So you have all these tools that convert between one and another. And then I've put Wigzel, the web GPU shader language, kind of intermediate between a high-level language and a low-level language. It started life as essentially a textual representation of SpireV. The idea was that it would be bijective, that anything you could express in Wigzel, you could express in SpireV, and vice versa. They've been diverging a little bit from that, but it's still, is a pretty low-level representation, and I wouldn't be surprised if Wigzel was primarily a compilation target from other shader languages rather than people writing directly in Wigzel, but we'll see. We will see. So, this is showing the kind of basic execution model of how you get work done by compute shaders. And so there's a bunch of things going on here. The main thing is that there is a host thread on the CPU. Obviously, there can be more than one host thread, but this is a simplified picture. So there's a thread running on the CPU, which is dispatching the work to the GPU. And then there's another thread, or it's not a thread, it's called a queue. And again, in this picture, I'm showing one. You can use more than one queue. You don't have to. You can actually exploit most of the power of a GPU just with a single queue. And a queue is conceptually a sequential timeline. In practice, it's more complicated than that, but it's a good way of thinking about it, that it's running a sequence of operations. And the first operation that you're going to do generally is copying that buffer that exists in CPU host memory to the GPU. And then when you have dispatches, so the dispatches are grids of basically function calls, programs that are operating in a grid of threads, and those read and write those buffers, that those dispatches are primarily going to be accessing memory on the GPU, buffers that are allocated in GPU memory. Then I'm showing these little vertical ticks. Those are pipeline barriers. So you have to do synchronization, that if one dispatch writes something and another dispatch reads it, then you have to place a pipeline barrier between those to avoid overlaps, to avoid hazards of things reading from cache that hasn't been flushed and so on and so forth. It's one of the things that makes GPU programming exciting and interesting. And then if you're doing compute tasks, then you're generally going to do read back. You're going to copy the buffer that was written by those dispatches back into GPU memory. So then that completion, when you're done with everything, that's asynchronous. So there's usually a fence that you wait on, or there's some sort of asynchronous future that says the result of that computation happens asynchronously after dispatching it. So in this slide, I want to get across rough performance numbers. Like detailed performance is out of scope for this talk, but I wanted to get a qualitative sense of how kind of what to expect, what numbers to attach to some of these things. So the first thing is like motivating that choice of copying buffers to the GPU and having the work done on the GPU in GPU memory. There is more than an order of magnitude difference typically in the PCI bus bandwidth for the GPU accessing host memory, which is 32 gigabytes per second on a pretty decent, powerful desktop GPU. I have an AMD 5700 XT that I use for these numbers. So that's around 32 gigabytes a second, and then the access to GPU memory by shaders is half a terabyte a second, which is considerably higher. When you do dispatches, those dispatches are going to be run by, in this card, which is pretty typical, 2,500 threads. And you actually want those dispatches to be more than that. You want to have multiple threads that can run so that you can take advantage of the latency hiding capabilities of the GPU. But if you have a pure compute workload, each physical thread can generally do a multiply in and add per clock cycle, and you've got around 2 gigahertz, round numbers. So you end up with approximately 10 teraflops of compute bandwidth, which is really a lot by almost any standards. And that's an interesting thing, that if you multiply that by the amount of overhead that you have to submit work and get the completion back, that's approximately 100 microseconds. There are a lot of kernel transitions back and forth. It's a pretty heavyweight operation to dispatch work and get it back. And so if you're not doing a billion floating point operations worth of work in that compute dispatch, you are not utilizing the full power of that graphics card. And so you really want to pack as much work as possible in a single dispatch. If you have a model where you're kind of organizing the work on the CPU and you say, okay, I've got a little bit of work I want to do on the GPU and then wait and read it back, and then a little bit more work to do on the GPU and then wait and read it back, that is not going to give you performance. You need to batch the stuff up, do upload stuff, have as much stuff happening on the GPU, accessing resources that are resident on the GPU as possible to get that performance. So now I'm going to go through a little bit of the mechanics of how you get to the GPU, how you get work running on there. And if you haven't done GPU programming, this is just bewildering at first. And later I'll have linked a glossary which explains a lot of the terms and kind of motivates a little bit why you need them. But I'll go through it real quickly here as well. So the first thing that you get is an instance. And an instance is really representing the API. And like in all of these levels of abstraction, they exist largely because there are multiples of them. That if you're on a Windows machine, you might connect to Vulkan, and your instance might be a Vulkan instance, or it might be a DirectX 12 instance, or it could be DirectX 11, or it could be OpenGL for compatibility reasons. But that's the first thing that you do, is get that instance. And in practice, that means populating a lot of function pointers, which do the actual operations. Then once you have your instance, you need to get to the physical device, and there can be multiple of those. On a laptop, you might have both an integrated and a discrete GPU, and so you might need to do some logic of maybe they have different power requirements. Maybe one is more efficient than the other. Maybe you just want the highest performance. And so there's some negotiation there about how do you choose an adapter, or perhaps you want to be able to run work on multiple adapters at the same time. Then from the adapter, you get what's called a device, which is a very overloaded generic term. But in this context, a device is the scope for creating resources. So you allocate your buffers, you allocate your images, you get your shader programs compiled, and you also, from the device, create a queue, of which, again, there can be one or there can be multiple, depending on how sophisticated you're trying to be. And the queue is the unit where you submit work, where you cause these dispatches to happen. And the use of multiple queues is often known as async compute. It allows more overlapping. It allows you to get work done when some other pipeline stage might be stalled, but it is not strictly necessary to get pretty good performance. So just this ceremony, just getting everything working. If you're doing it in Vulkan, it's at least 200 lines of code for the basic version, and this is also where you generally do the runtime detection of optional features and capabilities, and all of that is a lot more code to do right. Makes it much more complicated. But if you're doing it in web GPU, then typically it's 20 lines. At each of these stages, get the instance, get the adapter, get the device, get the queue, is about 5 lines of code. So it's much more straightforward. But of course, there's still a lot more to be done before we can actually run anything. Now you have to create those buffers. And on Vulkan, it's a very complex process. There's a lot of control of the fine-grained details, and most people use a existing library like the Vulkan memory allocator. In Rust, there's a couple of choices: GPU alloc, GPU allocator, that manage that low-level allocation for you. The most important distinction is whether you're allocating a buffer on the host, so it's accessible to the CPU, or on a device where it is not generally accessible to the CPU, but has much higher performance when you're accessing the buffer from shaders, from GPU operations. There's a lot of complexity to this. It is also evolving that the CUDA idea of unified memory is making its way to compute shaders as well. The feature to look for is resizable bar. It's a relatively new feature, and I'm linking. If you're curious about that, I'm linking an article on Vulkan memory types, which talks about resizable bar, and that goes into a lot more detail. But the thing about Vulkan is that you don't allocate individual buffers from the API. You allocate slabs of memory, and then you sub-allocate. Like if you want to allocate hundreds of buffers from a 256 megabyte chunk, that's a lot more efficient. So that's one of the reasons why there's this complexity. Yeah, and so again, going back to this, that in Vulkan, a fully featured high-performance allocator is thousands of lines of code. You can look at the VMA repo. And in WebGPU, all of this is hidden from you, that you just call device.createBuffer. You give it a few flags. They're called usage flags that say, are you going to use this for CPU access, yes or no? It's really about one line of code. So creating the buffers, we're still not done. We still need to deal with the code. And so this is where compute pipelines and descriptor sets come into play. So a compute pipeline is basically your compiled shader. So in Vulkan, your source code for that shader would be in SpireV format. In WebGPU, you would write the shader in Wigshole, which is similar to SpireV, but a textual format. And then you give that to the API. The API compiles that to the actual code that's going to be running on the device. But this choice of compiling from your source to your intermediate representation, that can be done at runtime, which is required on web GPU because you're going to be downloading that potentially malicious code from the web. But if you're shipping an application, you have a choice of compiling it ahead of time and bundling the intermediate representation into your program. And that actually, that's going to make your program smaller because you don't need to pull compiler infrastructure into your program, and makes your startup time faster. So that's one of the trade-offs. And I'm jumping ahead a little bit, but that's one of the major motivations for why Peak GPU HAL exists, is to support that ahead of time compilation of this shader source, whereas WebGPU really insists on doing it at runtime. So the shader source specifies when you look at shader source, it has these blocks called layout that tell you what buffers and images it's going to be accessing. And traditionally, it's a small fixed set of buffers and images. But if you have descriptor indexing, which is a newer optional feature, then that might be an array of buffers or an array of textures, and that gives you more flexibility. The array of textures is primarily used in ray tracing, where in kind of traditional GPU, each draw call is accessing a small number of textures, but in ray tracing, if you bounce array, it could be going anywhere in the world and accessing textures, potentially a large number of textures. And I was waving my hands to show the bouncing of the rays, and now you can see it. So then there's this idea of a descriptor set, and so the layout says what kinds of buffers you want to access, but the descriptor set says, okay, for slot 0 in the layout, I actually want it to be this buffer, which I allocated. So you create a descriptor set. In WebGPU, this is called a bind group. In DX12, this is called a descriptor table. Again, go to the glossary. It's very common for there to be slightly different terminology. It's very confusing. But that's what the descriptor set does. It says, these are the resources I'm going to use so that when the code runs, it's going to be reading and writing this set of buffers and integers and images. So you can think of it as a set of capabilities that the code by itself can't just access memory through pointers. It can only access memory through these descriptors that you give to it, and descriptor sets are the way to create that. So now we're ready to run the code, and that's done in a dispatch. So a dispatch is your compute pipeline, which is your compiled shader, your descriptor set, which is the buffers and images and possibly other resources that that code will be operating on, will be reading and writing, and then you give it the size. So that's an XYZ grid, a 3D grid of work groups. That tells you how many work groups to run. And then conceptually, when you do multiple dispatches in a queue, conceptually those are running sequentially. As always, the truth is a little bit more complicated, that there might be some overlap. If you're using Metal or WebGPU, then it will basically give you the abstraction of running those things sequentially, and it will do the synchronization. It will insert the pipeline barriers for you. And if you're doing it on Vulkan and DX12, which are much more explicit in flavor, then you have to be aware of when there are hazards and add those pipeline barriers explicitly and do explicit synchronization yourself. And then within a thread, so the dispatches run conceptually sequentially, but within a dispatch, then all of those threads are running in parallel. And there's a very large amount of parallelism that's provided by the hardware. There may be some scheduling, there may be some sequentialization, but you can't really rely on it, that you have to be thinking about all of these threads running in parallel. So let's talk about these threads and the way they're grouped, because there's an explicit memory hierarchy and there's an explicit thread hierarchy that's very parallel to that memory hierarchy. So the lowest level of that hierarchy is a thread, which is called, if you're the kind of person that likes to use the word octet instead of byte, then you want to call these invocations. But they're called threads. And so then the next level of grouping is called subgroup in Vulkan, or warp or wave or Cindy group, depending on which API you're using. And these are the threads that are run kind of in one clock by one execution on the device. So it's very analogous to the Cindy width of a CPU. It's always a power of 2. Most common values are 8 through 64. If I look at the devices in front of me, Intel integrated is 8, Radeons are 64. It goes down as small as 4, it goes up as high as 128, but those are rarer. And you do have to know the size of the subgroup when you are doing explicit subgroup operations, which are faster. They're lower latency. They basically allow communication between threads through these subgroups without going to memory. So again, when I was going through the memory hierarchy, that because you can use these registers to communicate, that's more memory-like than register-like. And you also want to know the subgroup thread for the subgroup size for performance reasons, because it affects divergence and other things. I will go hopefully into more detail on that in the performance talk, which this isn't. So the next grouping of threads is the work group. And in general, anything larger than the subgroup size, but smaller than the device limit, which is usually 1024 on desktop, but it can be smaller on mobile, is good. And the work group is really the primary grouping of threads for the programming model. And I'll go into more detail, but the main reason is that threads can communicate and they can synchronize within a work group, but they cannot at any larger granularity than that. And then those threads, the workgroup threads, are organized in a dispatch, and a dispatch needs to be thousands of threads, possibly tens of thousands, in order to utilize the parallelism that's provided by the hardware. So I have a question on chat. What is the relationship between subgroups and workgroups? This is the organization of the threads. That the subgroup is a smaller cluster of threads that within a subgroup you have access to higher performance, lower latency communication between the threads. So when you're programming, you have to be aware of that hierarchy, of the way these threads are organized, so that within the smaller clusters you get higher performance, more tightly coupled integration, and in the larger clusters you have larger scope. You can communicate with more threads, but that communication is going to be slower. I hope that answers that question. So subgroup size. I spent a lot of time on this, figuring it out. When you are programming with explicit subgroups, your code is sensitive to the subgroup size. You do not generally get to control the subgroup size. It depends on the hardware, and in some cases the compiler. So this is a huge complexity for portability. And on NVIDIA, it's very simple. The subgroup size is 32. And so that is one of the things that makes programming CUDA easier and portability harder. You can avoid worrying too much about subgroup size by focusing primarily on workgroups and workgroup shared memory, which is the next topic that I'm going to go into here. And so workgroup shared memory, again, this is one of the concepts that is not really something that exists on CPU. This is a new concept if you are doing GPU programming, that you need to access workgroup shared memory to get high performance interaction coordination between the threads of your program. So generally, this is a small area of memory. 32 kilobytes is the typical maximum, and you usually want it to be smaller than that because it might affect occupancy. It might affect the number of workgroups that can be running in parallel, because that's a very limited resource. It's a very high bandwidth piece of memory. It's expensive. It would cost a lot of power and silicon area to make that larger, which is why it's that small. And it's much faster. There is much more throughput because all of the workgroups can be accessing their own local, their own dedicated piece of shared memory. They don't have to be going over the global memory bus. And the latency is also similarly much smaller because it's much closer. It's usually physically close on the chip to the execution unit, whereas memory is over a very long bus. The relative performance, it's interesting. On some GPUs, the shared memory is not that much faster than going to global memory. In some cases, it uses the same mechanisms to implement it. And on others, it's just lightning fast, that it's just right there. It's super fast. So you do need explicit barriers to synchronize access. So if one thread writes to shared memory and another thread reads it, you generally need a barrier between those to make sure that you're actually getting the value that was written and not having some sort of data race. And so you almost always are going to need to use workgroup shared memory to coordinate work from multiple threads. If you have an embarrassingly parallel workload where each thread can just do its own thing, like Shader Toy, where each pixel just computes its own function, then you don't need workgroup shared memory. But if you're doing any kind of shuffling of data or sorting or prefix sum or some of the other advanced things that are done in GPU, then workgroup shared memory is the main mechanism that you coordinate the work between the multiple threads. And the good news on workgroup shared memory is that all compute shader implementations have basically the same story. If you write code once that uses workgroup shared memory, it will generally run pretty well on any GPU hardware without a lot of compatibility headaches. So subgroups, I really recommend start with the workgroup shared memory and then use subgroups as an optimization later. Explore how much performance improvement you get and whether that's going to be worth the compatibility headache from doing that. So compute shaders are not quite general purpose programs, but they're pretty close. That they can do a lot of things. They can read and write memory using random access through the descriptor set. You can use atomic operations. You've got all of the basic compute primitives, your integer, floating point arithmetic, bitwise operations, branches and loops. It looks a lot like C code. You can do function calls. Those are optimized pretty heavily. You can treat that as an abstraction. And then you can access shared memory, which is this special feature that's generally not available on CPUs. And then you also have these subgroup operations, depending on portability. You can synchronize with other threads in the workgroup using these barriers. And you also generally have access to special GPU hardware, like, for example, bilinear filtering for textures. There's not a huge set of intrinsic functions, though, that are unfamiliar to CPU programming. There's also things that are not available to compute shaders. So you can do function calls, but the stack essentially is fixed. You cannot do recursive function calls. You cannot do function calls through function pointers. So all of your kind of object-oriented dynamic dispatch stuff is not available to you. You cannot synchronize with anything happening outside the workgroup. So that's why generally the synchronization is done dispatch to dispatch. You can do some things. You can do a spin lock. You can have an atomic that waits for some other computation to happen. And this is used in, for example, the decoupled lookback algorithm for prefix sum. But it's tricky. And the forward progress guarantees are weak. If you're interested in that, go to the prefix sum blog post. It goes into tons more detail on that. You cannot access memory other than what's mapped through the descriptor set. That's a set of capabilities. If those descriptors are given to the compute shader, it can access that memory. It can't just randomly access other memory on the device. That is partly changing. There are two flavors of pointers, they can be implemented either as real pointers, which let you crash your GPU in creative ways, or they can be kind of a layer over saying it's a descriptor index and an array index within that descriptor. I don't see pointers being used a lot in compute shaders, honestly. That may change. That may be something. I think they're primarily interesting if you are porting workloads from CUDA, where you have full access to pointers in CUDA. Very sadly, compute shaders cannot dynamically allocate memory. You pre-allocate. You estimate how much memory is needed before launching the work, and you can allocate chunks of memory, and then you can use atomics to sub-allocate within those chunks. And GPGPU does that extensively. But one thing you cannot do is say, hey, I actually need more memory for this. Go allocate that memory, come back. That is something you can do in CUDA. And then the other thing that you really cannot do from a compute shader is spawn other work. There's indirect dispatch, which gives you a very limited way to spawn other work, but for the most part, coordinating the work that is being done is dispatched from the CPU. The CPU needs to decide kind of the graph of work and dispatch it from there. So I want to talk a little bit about different levels of capability that compute shaders have. And level 0 doesn't even need a compute shader capability in the API. You can do this in WebGL, which is what I call the shader toy model, where each thread is doing its own computation, and it has random access read capability for texture inputs, and its output is one output per thread. And it's surprising how much stuff people can do creatively using this model, but it's not a real compute shader. It's a gateway to compute shader capability. So real compute shaders start at pretty much all of the graphics APIs, DX11, OpenGL 4.3, GLES 3.1, which is available on a large number of phones. Vulkan starting from 1.0 of Vulkan, and of course WebGPU will have this compute shader capability. And that adds the access to shared memory, work group level barriers. It gives you random read and write access to images and buffers, and it also gives you atomics for doing fancier things concurrently. So that's the basic level for portability. That will run on pretty much everything today. Newer stuff, the X12, Metal 2, Vulkan 1.1, adds to that subgroups, which are performance optimization and descriptor indexing, the ability to access arrays of resources rather than just some small fixed set. And then the newest level, which is in Vulkan 1.2, and really not a lot of the other APIs, give you explicit memory semantics, some kind of real pointer, and the ability to explicitly address, like consistently, reliably address scalars other than 32-bit. And so I think that's the one that's closing the gap on CUDA, that's giving you a lot of the capabilities. Obviously, it's still missing function pointers and stuff, but it's giving you a lot of the capability that CUDA has. So if you compare WebGPU versus Vulkan, these are two on-ramps that are both quite plausible. And WebGPU is much easier to get started. You can write your hello example in 100 lines. Vulkan requires you to go through all this boilerplate to set up the low-level details. WebGPU has automatic resource tracking and automatically adds the pipeline barriers. Vulkan makes you do that, but gives you a lot more control. So potentially you can get better performance. The shader language, WebGPU uses Wigzell, which is still in development. It's not quite there yet. And in Vulkan, there are technically a lot of shader languages you can use, but GLSL does have a privileged place in that spectrum, that it is the only language that supports all of the Vulkan capabilities, all of the optional Vulkan capabilities. So then in Vulkan, you can do ahead of time compilation to the IR, or you can do real time in your app, depending on how dynamic your workload is. In WebGPU, that compilation is always going to be runtime. And then one of the potential huge advantages of WebGPU is that you can deploy to web, whereas Vulkan is obviously native deployment only. So I have a question about random number generation. I think that's a super interesting question. I'm not gonna answer it on the fly. Maybe we'll do some kind of follow-up later. Very rich, complex question. So if you're going to use WebGPU, there are two major implementations today that are open source anyway. There's WGPU. It's totally fine. Don't worry about it. There's WGPU, which is the implementation that is used for Mozilla. And then there's also Dawn. I should probably give them more props, given that Dawn is the Google implementation that's used in Chrome. I'm using WGPU primarily because it's written in Rust, and I'm doing all of my research in Rust. And also, I think because Dawn is more specialized to being the WebGPU implementation in Chrome. I'm sure people can be used for other deployments, but WGPU I think has more uptake. There are projects like the Bevy Game Engine and ICE-D GUI toolkit that use WGPU, that it can be a native, a runtime for access to the GPU, portable access to the GPU for native deployment. WGPU has support for SpireD as well as Wigzell as the shader input, and it will do all of the cross compilation for that. And they used to use SpireD cross to do most of that shader translation. They've started a project relatively recently called Naga, which is a lighter weight, it's higher performance. It's not a big giant C++ dependency, and that's exciting, but again, it's not done. I have a question. When do I hope to see WebGPU land in stable Chrome and Firefox? I cannot, that's speculation, but let me just say, I am not expecting for that to happen anytime soon. There is a considerable amount of work that remains on both standardization and implementation and validating that it works. So if you're waiting for it to land in stable, you might be waiting a while. If you want to use it before then obviously you can use it off of the canaries and betas, or you can bundle it into your native application, as is done in like the Bevy game engine and so on and so forth. So I want to link now to some resources. Again, my main goal in this talk is to get people writing compute shaders. And here's a bunch of resources that will get you hopefully started on this glossary. The link is out there. These are all clickable links. Hopefully people can follow those. There's some really good samples for web GPU. The first link is web GPU samples. These are written in JavaScript and primarily designed to run on Chrome, but hopefully as the Mozilla implementation matures, it should be possible to do it on that as well. The second link is really, really interesting. It is a reimplementation of fast Fourier transform on Vulkan, and it really, one of the main points of this is to prove that compute shaders are capable of performance that is comparable or even better than CUDA. And so one of the other reasons that I link it is it targets Vulkan, but it doesn't target portability at all, and or to compute shaders. There is an OpenCL port in there and a CUDA port now, I believe, as well. But if somebody is adventuresome, if somebody wants to try doing something interesting, they might port VKFFT to either pGPU HAL or one of the web GPU implementations, and you'll learn a lot by doing that. You'll bump into some walls, but in theory it should be possible, and that should get you an extremely high performance fast Fourier transform that runs portably. There's a great tutorial also from the Chrome developer people on how to get started with GPU compute on the web. So that walks you through how to do a web deployment of compute shaders. Walks you through all the basics of how to create the resources and stuff like that. That's in JavaScript, targets web GPU, but the ideas will carry to Rust or other APIs as well. If you want to get started on WGPU, there's a tutorial that's quite detailed. That's mostly focused on rendering the rasterization pipeline, but it will get you started on WGPU. And then the last link on this page is a glossary of terms that defines and motivates like all these confusing terminologies. But the main thing that I want to encourage people to do as the next step, if you're interested, is that I've recently created this Compute Shader 101 repo, and that gives you 3 different starting points for simple kind of hello world experience for getting your compute shaders running. So there's a compute only version that's on WGPU, and there are 2 shader toy-like choices. One is running on WGPU, the other is running on pGPU HAL, and that gives you a choice of shader language. The pGPU HAL ones are in GLSL. And the shader toy example is pretty simple. The idea is that you can start with shaders from the book of shaders, or you can go to shader toy and adapt those. And that adaptation should be fairly simple. And this is level 0, but once you've gotten shaders running, it's a great starting experience, especially if you haven't done shaders before. Once you have those shaders running, then you can start thinking about, okay, now I can do something that I can't do on shaders. These threads can communicate. I can do blurs. I can do things that I can have pipelines of interacting computations that I can't do with just shader toy. But starting with shader toy is a great on-ramp to that. Now, if you're going to use the compute example, I have a blog post on prefix sum that goes into detail. That algorithm is pretty high tech. It's decoupled lookback. It requires atomics. It's not that easy. There is an implementation from Cub, which is a NVIDIA library on top of CUDA, that might be easier to adapt. And if you are going to do your own prefix sum implementation, I really do recommend it. It's a great starting point of using compute capabilities. A good warm-up, something that's really easy, is just sum all of the elements together in the input buffer. And then once you've got that, then upgrading that to do real prefix sum it's a good step in that direction. And I'm open to ideas. Like this repo exists. I want definitely file issues, PRs to improve it. But also, like, what are things that you want to do? What are good examples? Good starting points to motivate compute shader tutorials, basically. So that's the slides that I have. I'm now going to open it up to Q&A, and I have a couple of those. I have at least one from Twitch, and hopefully we'll have more. So I will read these questions. Are there any problem classes that seem like they would parallelize well, but that are difficult or impossible to solve effectively with GPU compute? This is the core question. So there are a lot of ways to answer this, and one of the things is that there is a lot of academic research on this question of how do algorithms parallelize. The idea of parallel computers have been around for decades, and they've been pretty theoretical. People haven't had access to highly parallel computers until recently. But there's all this research on prefix sums, which again, it seems like prefix sum is just like sequentially adding, but in practice you can do it in parallel tremendously well. I've got some blog posts on that, and yeah. And then there's also experience from the graphics world that there are some data structures, like somebody just mentioned on chat, bounding volume hierarchies. These are used extremely extensively in graphics and in rendering, and that is a data structure that it turns out that compute shaders can access very, very efficiently. So there's some data structures that are efficient and work well, and there are others that are challenging, and I think that we're going to continue to evolve, figuring out what works well on GPU. My personal sense is that there are a lot of algorithms that people think of sequentially that actually can parallelize pretty well. Like one of the other things, I don't have it linked from here, but really interesting is CodeDFNS, which is a full compiler, parser, everything, written in an array language that is designed for efficient GPU abstraction. So I think this is a boundary. Like, what can we do efficiently? We're going to keep pushing that boundary. Yes, and that's the same thing. Can you use more complex data structures like trees, quadtrees, etc. inside a compute shader? Absolutely. So these are general purpose computing programs that can access generally arrays instead of pointers, but you can do very pointer-like things like traversing a linked list. Now, if you have a long linked list, that's not going to be efficient. Sequentially traversing that is going to be painful. So you want to do things like B trees, where you can possibly extract parallelism by being able to access all of the children of a B tree node in parallel. But yeah, in general, the full palette of data structures is available to you, and it's just a question of figuring out what works well on GPU, what's actually efficient when you're accessing it in parallel from lots of threads rather than having a single thread accessing it sequentially. So the compiler is CodeDFNS, and it's done by, I think, IndieShu, HSU. I don't have a way of creating links here, but hopefully CO-DFNS. Aaron Shu, thanks. Yeah, I had a feeling I got that wrong. Is there a strategy to parallelizing problems you've seen so we can leverage a GPU, or is every problem unique? I think there are strategies, but I don't think there's a single generic strategy. I think you start with looking at what is the inherent parallelism in the problem. There's some problems like interpreted languages where extracting that parallelism is going to be extremely challenging. Graphics rendering problems, you usually have a lot of inherent parallelism because every pixel can be computed effectively in parallel with every other pixel. So, and then you have things in between, like if you're doing prefix sums or these stack monoid things, where there is parallelism, but you have to dig a little bit deeper to find them. So my hope is that we're going to evolve more of a toolkit for how to extract and exploit that parallelism. There is also a lot of work in the CUDA, like compute shaders. The problem of how do you make compute shaders run performantly is very similar to the problem of how you make CUDA run performantly. Great. How do you handle problems which need dynamic resource allocation? Yeah, I spoke to that a little bit. This is a little challenging, and so it's going to be a mix where, first of all, you estimate the resource allocation up front. That's what games do. Games have usually a pretty well-defined problem space. You usually know what you're going to be doing. So I think in most cases you can say, okay, to render this scene, I'm going to need 128 megabytes, and I'll use testing to validate that that will always work. One of the other choices that you can do, and this is done a little bit in PGPU, it's kind of half implemented, is that you can allocate with an atomic pointer. You can have a begin and an end, and you can say, all right, if you cross end, your allocation fails. So you basically say, have a flag in your shared memory buffer or your global memory buffer that says allocation has failed, and then you can read back. You can wait on that and see, did allocation fail? Did an allocation cross the endpoint? If it hasn't, then you're good. If it has, then you might be able to re-dispatch. You might be able to either, in the case of GPGPU, you might say, I'm going to allocate a smaller slice of the viewport and dispatch only into that smaller slice, so it'll take less memory. Or you might say, I'm going to ask for more memory and rerun it with more memory. Not always efficient. That waiting on that fence and reading back to check and see what happened is something that takes time. So, but there are workarounds. The fact that there is no malloc call from inside a compute shader is friction, but not a complete brick wall. What do I think about Rust GPU? Do I think that is a valid direction to write compute shaders? Yes and yes. I am very excited about Rust GPU. Compute shader capability is new and evolving, but I think that if it can be made to work well and portably and performantly and access the capabilities that are there, then I'd much rather be writing compute shaders in Rust GPU than in a C-based language. My blog post on decoupled lookback prefix sum is brilliant, by the way. That's not a question, but thank you. I appreciate that. That's why I write the blog, is to try and get this information out there. It's really good to hear that people are enjoying that. APL-based GPU languages. Yes, APL array languages have been around a very long time, and because they work on these 2D arrays or multidimensional arrays that with kind of a grid structure, and because the operations in those languages are essentially parallel, they adapt much more easily to GPU than traditional sequential languages. So I think there's a lot there. My personal beef with array languages is, like, if you have scan, which is written as a slash, you can say slash plus, and that's a prefix scan, which is fantastic. But if you say, I have a monoid that I designed that I want to do, like a finite state machine or something like that, it's very much harder to say, I'm going to run this scan operation over this general purpose monoid. So I actually have hope. This is the place where this is getting into speculative territory, but what I really would love to see is that you have prefix scan, as a generic library that you call, and it takes a trait, which is monoid, and then you just mix and match. So do you want tree reduction prefix scan? Do you want decoupled lookback? And then on the monoid, do you want just plain sum? Do you want a state machine? Do you want a stack? You plug it in, and it just does it. Now, whether we get there or not is a little too early to say, but potentially that's something that would be very hard to express in APL, in an array language. Can cycle be ported to Rust? I don't know. I mean, this is a very complicated thing. This gets you into to what extent are you porting existing code, and to what extent are you greenfield? My personal feeling is that you're going to see most of the activity, most of the progress in greenfield things where you're writing new things. Porting existing things is very complicated. There are a lot of assumptions that get made. It's not that it can't be done, and there are good motivations to do it, but that isn't where I would be spending energy right now. Is now a good time to ask about RNG and compute shaders? For context, I'm interested in parallelizing Monte Carlo simulations in compute. Yes, now is a good time. So if you just want pseudorandom numbers for things like simulations, yes, this is really easy to do on a GPU. That one of the ways, like there's a huge literature on PRNGs, but conceptually one of the ways to think about a PRNG is that it is a hash on a sequence number. And there are a lot of RNGs that actually work this way under the hood. Like I think Soro, Shiro, and that family is a good one. What's the other one? There's something called split something. I can't remember. But there's a whole family of PRNGs that are essentially hash functions on a counter. And if you do it that way, then you can just do it in parallel. The counter is just sequential numbers, and you just compute that hash function completely in parallel, and that works brilliantly. There's another class of PRNGs, obviously, that's very sequential, like your jittered congruential. What are those things called? The feedback shift registers. The linear feedback shift register can parallelize because it's linear, but if you do the jittering on top of it, that makes it sequential, so that won't parallelize. So it really comes down to the same thing. Like you've got all of computer science, but some things parallelize great, like if you're just computing a hash function on a counter, and other things don't parallelize and just choose the stuff that parallelize. I hope that answers. And then Spencer linked to a recent article on computing hash functions. There's an excellent survey in the Journal of Computer Graphics Techniques that goes into in great detail about like what hash functions are high quality and perform well on the GPU. All right. Well, thanks everybody. This is actually my first time streaming a technical talk. I hope you enjoyed it. I appreciated having an audience. I appreciated having the chat while I was going. I think I'll wrap it up and post this to YouTube. And with luck, I'll be doing this again. I have more material. I have some stuff on performance that I hope will be interesting as well. And please do check out the sample code. Please give me feedback on what that experience was like. And feel free to file bugs, PRs, issues. I want to make that into a high quality resource. And you're kicking the tires will help do that. So thanks again for coming, and hope to see you soon.